provided a lot of basically abstractions for I have core utils there, but whatever application you want to run, it and we can see through the ubiquity of Linux how that fostered innovation. So it's unusual to get a device without Linux now these days. So the amount of innovation and ease of development that fostered, OpenStack kind of sits in the same place, or it has the potential. Maybe not OpenStack, but it's well positioned to take the lead in this. But a project fulfilling OpenStack's functionality abstracts you away from at a higher level, and basically gives in the cloud space the same innovative abstraction that the Linux kernel gave in the device space. So I'm not going to go too deeply into OpenStack, but I'm just going to give an overview of its structure so as we can see where Python technologies would fit in to implement each of these bits. So it's split into separate projects. There's Nova. Since it's originated in NASA, they have names like this. But so Nova is your compute service. There's an object storage service called Swift. Glance is a fairly simple service. It's for just managing the large guest images and providing them to Nova. Keystone is the central identity and authentication server, so that supports public cloud and private to some extent. Horizon, there's a web GUI to drive all these services, and that's implemented in Django, as we'll see. Quantum is the networking service. So all these services, but Nova is the central one. So that's where everything falls out of. It's all centered around controlling the hypervisors. And so as the project evolves, things tend to be abstracted out of the Nova service. So Glance came out first, and then Quantum is basically abstracting out the network control for Nova, and it supports things like software-defined networking. So it has plugins available for Open vSwitch. So that's trying to virtualize networking infrastructure in the same way as hardware standard servers infrastructure were virtualized by KVM and stuff like that. So, for example, software-defined networking that has a lot of benefits as well. I think Google announced a while ago that they've switched their internal network to a software-defined network. They built their own hardware and everything because of Google scale and stuff. But the interesting part is that they've abstracted the networking part into a software basically. So it gives them more control. So it's a general trend really, so that things are abstracted higher and higher up into software, so you can give more control. The volume service, that's akin to EBS, the Elastic Block Store in Amazon. Okay, I won't go into that, but if it's basically conceptually how the different OpenStack services talk to each other. If you're interested, you can have a look. This is worth talking about. It's for three reasons. It's Wikimedia's implementation of OpenStack, and as I said before, they're long-term users of OpenStack. And the first interesting thing is the way they've implemented their system. It's completely abstracted out into use Puppet modules that are committed in, and it's completely automated then how the system is provisioned. So everything is, they have their own private cloud, and things are provisioned using OpenStack in that. So, and they give different levels of controls to people. So it's definitely worth looking. If you see the bottom URL, you can follow that there. It's a very interesting setup, and it shows some of the flexibilities of using and things you can do with OpenStack in a private cloud. The other thing you can see here is how you can split out the OpenStack services onto separate systems. So the OpenStack services are scalable horizontally, so within a node, or you can, because they're all, you'll see later how they're all connected up, they can all sit on separate systems. So you can see how they group things in Wikimedia there, the green being the OpenStack services. And another interesting thing to note about Wikimedia is they use Jenkins and Gerrit, and the OpenStack development process uses those as well. So I'll get into those in a bit of detail. Not going to go into this too much, but this is just to dive into Nova, the central OpenStack service, a little bit more to get an idea of the technologies it interacts with and what Python projects it would use then. So, interesting thing to note here is that you can scale each of the services horizontally. So you can run as many instances as you want. Each of there's two. This is the Nova service here, or excuse me, the Nova project, which is implemented using different services that can run within a single host or multiple hosts. And there's how you interact with OpenStack services from the outside are through HTTP interfaces, through REST interfaces. So you can see as Nova needs to get VM images from Glance, it'll get those over HTTP. So I'll go into some of the Python projects used to implement that. And then within Nova itself, the different services communicate through AMQP, which is it's a standardized message passing protocol. So it's a defined wire protocol and interfaces as well to implement that. And Cupid is shown there that you can have RabbitMQ, and that's another aspect of OpenStack. It leverages a lot of Linux technology, so it also supports many different flavors. So you can use RabbitMQ, ZeroMQ, or Cupid to implement the message passing. For example, the central database can be Postgres or MySQL or SQLite for testing, and I'll show how that's abstracted out as well. Don't need to say anything else more about that. Just a quick note on scalability. On the previous slide there, you've seen that the database was a central component there in Nova, and that can be that's a relational database, so that can be a contention point for scalability because of shared state and stuff. So the way that's scaled out is that about 500 compute nodes around that level of scale will talk to one particular DB instance, and then you can scale that out in a hierarchy of cells to scale up from that number of compute nodes. Okay, so who develops OpenStack? Take this slide with a pinch of salt. I couldn't help some shell foo, but it basically pulls down the authors list and counts out pulls out the email addresses and counts them. The bottom one there being Gmail, so definitely take this with a pinch of salt. But you can see there, Rackspace are central contributors. Citrix are interesting. They were contributing a lot, but they've pulled back now and they're concentrating on. They still contribute a bit to the Zen side of things, but they've pulled back and they're concentrating on their own cloud stack project. So I'll describe that a little bit. Red Hat are big contributors. And HP as well, so HP are implementing their public cloud in it, so they're large contributors. And it's worth mentioning as well Ubuntu and Canonical here, so you can add those together, and so they're big contributors as well. So what Python technologies are used to implement all this? So some shell foo again. So in my Git directory, I just iterated over each of the projects and pulled a bit of information out of pip requires. I set it out the comments and counted them, and this popped out. So the interesting thing here are the numbers here represent the number of OpenStack projects that use each of the Python components. So you can see here 4 on eventlet. So eventlet is used to provide scalability within each service. So it provides concurrent programming primitives, so you can run things asynchronously within a service. Other interesting ones there are paste and paste deployed. So that's WSGI abstraction. So you define in an ini file basically how to wire up WSGI apps through their URIs and connecting them into the applications. WebOb is used, so that's just another WSGI abstraction. So these are all in the part of the Nova project, just implementing the HTTP REST interfaces. Routes is the Python equivalent of the Rails routes, so redirecting URIs out like that. And let me see what else is interesting there. Yeah, well, it's worth mentioning Django. Django is used by the Horizon project to implement its interface. And, I actually forgot to include a screenshot of that, but it's a fairly functional interface for controlling all the OpenStack services. Probably not worth mentioning anything else there. Okay, so given all those Python projects, it's worth stressing the advantage of consuming the OpenStack project through packaging. I'm a bit biased here because I'm the Flora packager for OpenStack, but it does attract a lot of the details away from you. So you can just yum install OpenStack or apt-get install OpenStack, and it gets rid of a lot of the details. Pip has issues installing certain packages, like I've Python libvirt highlighted there. That's not actually part of the pip requires because it's a compiled up package. So it's a little bit awkward to install that into virtual env and stuff like that. So all those sort of details are handled by your distro packaging. And they're a good way to get an overall position of the project and the amount of technologies, Linux technologies that are leveraged as well. So I used a little bit of shell foo again here. So for each of the projects, basically draw out a graph of all the dependent packages. And now I'm going to, this is the first time I've ever used a Mac, so I have well, it's not that interesting, so I'll just describe the it's a big graph of basically every Linux package ever, but it's a
okay, I'll move it for you. Just
Okay, just kind of scroll quickly across to give an idea of the different. Each node there represents a package, and some of them are quite. It goes the whole way down to glibc. Everything uses glibc, of course, but it just gives an idea of the leverage that even though OpenStack is only 300,000 lines of code, it leverages a lot of technologies. So it is sitting in scroll quicker. So it's sitting in technology-wise. It's sitting in a sweet spot for the amount of stuff it can leverage. So thank you, Mr. McMahon. Okay, so getting into the development of it now. So it has a 6-monthly release cycle, and after each release, there's a design summit to figure out what to put in the next one. And so it started 2 years ago. So you can see the way it's named there. You pick a keyword that basically starts with the next letter. And you can see as well how the project has evolved with the basically things being abstracted out of the central Nova project out to the separate, and they're separated out into separate projects as things go on. So Lance has been added early on, and in the next release, Quantum, the abstracted out networking service supporting software-defined networking and stuff like that, that's going to be integrated as a core project. And also the volume, the EBS-like functionality is being abstracted out into central core project as well. Oh, I knew someone had asked that. That was that was Bexar, and it didn't follow the nice 6-monthly cycle, so it didn't fit in the slide. But it was kind of, that was a fix-up release. So, good question. I don't know. That's bad. So, development. So everything is done, all development happens on trunk, and it's always open. So as a release happens, it's done to a stable branch. So it's branched off, and then any stabilization work is done on the stable branch. And after a release, fixes are continually backported to that stable branch. There's standard tools used across all the projects. So that's Nova, Lance, Quantum. And the central tools used, Git is used throughout, which is great. Git, I really like Git. I really didn't like it at the start, but I really like its ubiquity now. And you really need to know Git. It's great. The interface is interesting, let's say. It's evolved rather than being designed, but the central core technology is absolutely fantastic. Garrett, that's another. That's a project that came from Google. It's implemented in Java. And it's basically a patch review system that came out of the Android project, so that's used. Again, just to cast your mind back to Wikimedia, use these tools internally as well for their implementation. And Jenkins is the central contiguous integration platform used in the OpenStack project, and that's implemented in Java as well. It's quite an intricate system they've set up, and that's a presentation in itself to go into the details. So I won't go into much details on that, but I'll give an overview of how things are how a patch filters into the system, basically. So the commit process, you You create your own local topic branch, commit it. There's a commit hook automatically inserted by Gerrit. So to interact with Gerrit, you install this Git hook, which all it does is it generates a hash and it puts it in the change ID. So it puts that tag in your commit message. And that allows Gerrit to track that change through the system. So as you change and amend your commit and push it into the Gerrit system, it can track it like that. So each project has unit tests. So you just interact with those with the shell script that sets up a virtual env, and that's cached, of course. And it uses nose to extend the standard Python unit test a bit. And PEP 8 is enforced using that project there. So PEP 8 are it's basically Python style guide. So white space formatting and stuff like that. So all the code going into the system, and that's been enforced very early on. So it's a slight annoyance for each patch you do when you add 2 spaces between class names and stuff like that. But it does give the code a consistent view, and it's easier to work with generally. So it is worth the slight annoyance. So then, when you've done your patch, you use this Git review tool, and this was actually developed by Openstack, and other people are using it now. It's not OpenStack specific. So you do Git review. It sorts out where the Gerrit Git trees are, essentially, and the stuff that you need to push it. You can use Git review -v to see all the Git stuff it's doing, but essentially it just pushes it up to the right Gerrit Git repository. Yeah, you can't really see that. It's not important, but that's the Gerrit interface. So if you go to review.openstack.org, it shows all the pending commits, and you can see there the subject. That's just the standard first line of a Git message. It's worth pointing out. I think I've noticed a bit people using Git that they don't put much effort into the first line of their commit message, and it's quite important. It's the most important part of the commit message, and it's used by a lot of tools to present interfaces like this, even Git itself through short log and stuff like that. So that's one Git tip I'd give anyway, is to keep a short and concise but meaningful commit message. Less than about, say, 50 to 60 characters is a good one. As you can see, who's committed it, what project it's committed on, and then on the far right you can see who's given it a thumbs up or thumbs down, and there's also a verified column there for the automatic testing tools to give the patch a thumbs up or thumbs down as well. If you drill into one of those, yeah, that doesn't come out very well either, but if you drill into one of the commits, basically Gerrit will give you facilities for adding comments to particular lines in a commit. On the commit as a whole, it gives a diff viewer. So it's a very functional system. It has issues with patch sets. If you want to break up larger changes into a patch set, it doesn't track those very well. It does have dependencies. You can see this automatically rolled up dependencies, and in there will be the other patches in your patch set. So it's a bit of an add-on. They're working on improving that, but otherwise it's a fairly functional system, and it works well. I like it. It also has, you can see, links into other systems there. So there's links into the bug tracker. There's the blueprints, which are just high-level documents. So it automatically links to those. And you can see the change ID highlighted there. So that's the ID that's used to track the change throughout the system. So the review process, anybody can plus or minus one, and each project has a core set of maintainers that can approve or disapprove of a patch. So the automated tests that get run on each commit, it's a very complicated system and in danger of becoming self-aware really at this stage. It uses OpenStack itself to instantiate instances like, for example, it will start up instances based on Python 2.6, which is the minimum Python version supported by OpenStack. It will start up instances based on 2.7, Zen, KVM, on bare metal. You even have stuff to start instances up on bare metal. It can start up everything on a single node, or it has recipes for starting up multi-node OpenStack setups. So there's a huge amount of testing there. I'm not going to go into detail. That's a talk in itself on how all that's set up. But in summary, how Jenkins processes through all these jobs is when a patch comes in, there's a pre-merge tests, it merges, and then it does the post-merge tests, which tests, it runs through the automated tests and then all the functional and integration tests across all the systems. I'm going to, the details here aren't important. It just gives an idea of the number of commits and the number of committers that the system supports. So you can see the different projects there. This is just picking a particular week, and it's just showing who has committed. So you can see the different. That's the networking. Swift is the object store. Tempest. The manuals get a lot of work in OpenStack, which is good. Nova, being the central service, still gets most of the commits and most of the work. So this system supports, there's a lot of developers continuously developing on it, and it supports them well. The Jenkins over the last few weeks has had a few issues, stability issues with false positives. But it's getting stable again. It does need a bit of, well, I think that's a function of the complexity of the system that's implemented at the moment for OpenStack, but it does require a lot of ongoing maintenance. Okay, so now stepping a bit outside OpenStack, I'm going to describe some of the related Python projects that support it. Support not just OpenStack, but fit well with OpenStack. Oz is an interesting one. It's written in Python, and it basically is a set of recipes for taking a standard install ISO and generating an image to run on a guest. Time is flying. So I'll quickly go through the rest of these. So it basically it generates guest images that can be run on OpenStack, or it can be run on Amazon as well, or wherever. So it's an independent project, but it fulfills a common need. And you can install packages or run custom scripts, or basically customize your guest image in a myriad of ways. So Rackspace cloud builders use it to generate a lot of images for use on their public cloud, for example. And you can follow that link there to get examples. And that's the link. I suppose at this stage it's worth noting basically how you get an install image the whole way through to running on within the cloud in OpenStack. So whoever, say, Red Hat release an ISO image, Oz will convert that into something that's runnable on a guest. You push that into Glance to store the image. Nova then, when you ask to to instantiate an instance of the image, Nova will pull it out at a glance, cache it, and then, as an example, you could use N here, but or KVM. But as an example, it uses Nova will use libvirt to start up that image on KVM. Another thing worth mentioning is this is getting back to the reliability of the cloud, and the Heat API is an interesting Python project, which is not solely worried about reliability, but it's more general. It's akin to AWS CloudFormation. So it's essentially a set of configuration for provisioning your cloud, provisioning all the services within your VMs, essentially. And because it has control over provisioning services within VMs, it's just with a little bit of extra logic with monitoring and stuff like that, it has it can provide high availability type functionality. So this it basically leverages attributes of the cloud to provide high availability by reducing MTTR, basically. So automatically, if something goes bad, then it can restart it really quickly, so your MTTR is reduced, and it also has functionality for escalating failures up. So, for example, if things fail 3 times within a certain amount of period on a VM, it will move the service over onto another VM. If all your VMs go down, it has functionality for moving them over onto a separate cloud. So it's an abstract service that supports high availability and provisioning in general. Cloud Init is worth mentioning as well. It's a Python project. It started in Ubuntu, actually. It's so basically concept here is quite simple. You install it within your guest, and you provide a config. So because there's no state associated with a lot of these guests, the way Cloud Init works is it pulls configuration from outside wherever it generates it on a metadata server, and defines things like installing packages and stuff like that to configure up the VM. Similar non-Python projects, so projects similar to OpenStack, it's worth giving them a quick mention. Overt is implemented in Java. It's more aligned with. That project is worth a look. Actually, it's very very polished, but it's more aligned with private data center applications. So things like it concentrates more on stuff like live migrations and applications like that. Eucalyptus, that's the one that Amazon have partnered with. That's implemented a lot in C. It's more concentrated. It's less general. It's more concentrating on EC2 functionality. And there's closed editions then to get support like that. CloudStack is Citrix's one that's in Java. Again, that has it's an open core model, and it has closed add-ons onto that. And OpenNebula is a similar project in C++, and again, that's more aligned with private data centers. Okay, so to try out OpenStack, you can go to trystack.org to register, and there's a cloud available there to try out instances of OpenStack on it. If you want to start developing it, there's devstack.org, which is basically a shell script to set it up. Or I would advise going through packaging to consume it, actually. So there's a link there for Fedora project. So it gives links then into setup guides for consuming and trying out OpenStack packages. And you don't even need a separate machine to try these out. You can run OpenStack within a VM, for example, and there's recipes for that. So clouds all the way down. Lots of jobs available in the space, so it's an interesting area. But we've seen the amount of Linux technologies that are leveraged by it, so it's a broad spectrum. So if you go to openstack.org, jobs, you can see there's 90 positions listed there by various companies, and there's 8 listed by Red Hat there, so you can go to details there if you want. More info. Yeah, so there are links. I'm not going to describe the links, they're obvious. So I've basically been describing OpenStack there, which is a service for essentially starting VMs. So Marek now is going to talk about a higher level project that runs within those VMs. So thank you.
Okay. Does it work? Awesome. So, do we have here some web developers? Guys, come on. Cool. Because what I'm going to talk about is OpenShift. I will start with what is Platform as a Service, because OpenShift is Platform as a Service. Because you are a web developer, you don't want to care about the server configuration. You don't want to care about operating system. You code your application. You want to deploy the application. And you want to have the application running. You don't want to care about this stuff. You want to have this stuff provided as a service. If you use infrastructure as a service, what is OpenStack, Amazon EC2 or something like that, you have to care about the servers, about the operating system. Because the infrastructure provides you with a virtual machine. Platform as a Service tries to relieve you from the pain of configuring, installing, and maintaining the systems. So you, as a developer, you can just code, you can push the source code somewhere, there is some magic box, and there's some magic there, and you have your application running. That's the basic concept. OpenShift is a project by Red Hat that implements this general idea. We have free version that is running on Amazon EC2, so you can use it for free. We have 3 applications for free, which you can use. Each can has half gig of memory, each can has 1 gig of space. I will show you a small demo how easy it is to deploy the application, really. It's running on Amazon EC2, it's on the OpenShift.com, and we support all these technologies that I mentioned here and a bit more. I even know people that are running COBOL there, so it's really flexible. So Python is here, Java and the hipster Node.js and this stuff, MySQL, PostgreSQL, MongoDB for the database backend. So if you use this OpenShift, it's Platform as a Service that does not lock you to the platform. You use the native APIs of these databases, and you don't have to lock yourself to some proprietary API that will not allow you to move anywhere else. Your applications still use the basic stuff. OpenShift is also open source. The open source project we call OpenShift Origin. It is hosted on GitHub. It is under Apache 2 license. The source code is freely available. We have a lot of tutorials. We have a live CD that you can just download, spin up using KVM, VirtualBox or something on your laptop, and have the Platform as a Service running there for some testing purposes. If you are ready with your application, you can just take and push the code to the hosted version and have it running in the public cloud. You don't have to care about the things between these ideas. So there are tutorials and live CD available at the OpenShift.com. OpenShift Origin, the open source version, can be run on OpenStack. Because you know now what is OpenStack is, you see that there are the tools that Padraig was talking about. You can use the OS tool to create an image for the glance that takes the OpenShift template to set up an operating system based on Fedora 16 that you can then deploy to OpenStack and have it running there. So the last command, the fifth, takes the final image and uploads it to the glance, that is image repository in the OpenStack. After that, can you see the image up there? I think it's not very much visible. That's the dashboard from OpenStack that you were talking about and you didn't have the picture. So this is the picture, not very visible. But from there, you can just start new node of the OpenShift origin, SSH into the machine, set up the broker that connects the node to the cluster of OpenShift that you are running yourself, and you have one node. If you need second node, just go to the 6, spin up new node, set SSH, set up, and so on. You can repeat the step and provide new nodes for deploying the applications. OpenStack automatically detects these nodes and uses them to scale your application, to provide space for the applications that you are deploying, and relieves you from the pain of setting these things, all these things, alone. So using these things, now I have 11 minutes. Using these things, you can have multi-node and multi-tenant platform as a service running on your hardware using OpenShift, OpenStack, and Fedora. So right now, you can have the OpenShift running on your own hardware using OpenStack. You can have it running on your laptop using the virtual machine using the live CD, or you can use the hosted version. Now, awesome. Now you can deploy the application. This is also a 5-step process. You can use the command line interface and you create new application. I give it name sample app and I use the type of Python 2.6. This command just slices part of the operating system in the platform. It spin ups the servers, it configures the system, it sets up new private Git repository that is used to transfer the source code of your application for your machine to the platform and allows you to deploy the application. The second step provides a MongoDB cartridge. Cartridge is something that you can run along your application to provide functionality the application needs. It can be database like MongoDB, MySQL, PostgreSQL. It can be cron. All these things that run along your application are called cartridges in this concept. The first step also clones the Git repository to your local machine. So in the third step, you just go to the repository, put your source code there, you git add, git commit, and you are done with developing. You push the code to the remote repository, and the application will be deployed, will be run, will be scaled, will be completely maintained by the platform. You don't have to care about anything else. This is the only steps you are supposed to do as a developer. The rest is done by the platform, right? So I will show you a small demo how it really works. So there I have OpenShift running in a virtual box on my laptop. This is the same code base that is running in the hosted version. It is completely the same. The interface is the same. I will just now deploy a sample Python application that uses the Django example. Because you don't have to change the application. You don't have to change the framework you are using. The only thing you need is to configure it. Yeah, like connection, database connection, like the data where the uploaded files are stored, and so on. So this is done by this template that we provide on GitHub. So I will use this template to set up Django application right now in the platform as a service that is running on my machine, and it's the same as would be like deploying to the hosted version. So I will go there. Can you read it? Yes, you can. So first thing is to create a domain. Domain is something like a namespace that is provided for your user. So I will use EuroPython, so EP, and the login name is admin. It wants a password. It sets up the SSH keys for me, so everything is, come on. Problem. Yeah. Yeah. So I have, where am I? Yes. I have the namespace created. The command successful. Okay. So rhc app create. I will create an application named example, and type will be Python 2.6, and the username is admin because I'm on my local machine. Right now, the platform as a service is slicing part of the virtualized Fedora for the application. It spins up Apache, it spins up VSGI server, it provides the SE Linux policies to secure the application, it sets up C groups to provide resource limitation, and this is done by the platform. As a developer, I don't have to care. I just create the application. Is it done? Not yet. So after this command, I will have a Python application template running. Hopefully. Might take a minute. Possible break-in attempt because I am importing the key there, and I'm here. Oh my God. So my application is running at example-ep.example.com. So this is running Python application that I just deployed. It's simple VSGI application that does nothing, just shows this simple template that says that you should put your source code in the repository and commit and push it there. So what I will do, awesome, is to import the Django template so we can deploy, yeah, it's here. So these are only two commands. I will go to the repository, I will clone the remote, I will add the remote one and pull it locally. It will override the already existing files, and I will have the application running. So, example. There's the Git repository, and I will pull it. So, you see that my template was imported. There are some Django-related files done, and that SQLite 3 database was also imported. I just push the code, to the platform, and the platform detected that there are pip dependencies, that it is installing Django right now, right? This is done, everything is done by the platform itself. You don't have to care about it. You just develop your application, you push the source code into the platform, and the application is running for you. So this takes some time because Django is quite big. 3 minutes. Nice one.
Wait, please. I was wondering why Django wasn't installed from a package. It was pulled down from the PyPy.
Because packages will be like operating system related, but the platform tries to isolate each application. So application may use Django 2.3, some application may use Django 1.3 or 1.4. So these packages cannot be like shared among the applications, right? So they can interfere. So each application has its own set of packages. So the applications are as much isolated as possible. Only the basic operating system is shared, and what can be separated and secured, that is separated and secured. So if I push F5, I will have my Django application running. If I go to admin, what's the default username and password? I don't know. I'm not a Django developer, so I'm not sure. But this is login to the Django administration console, and you see that the Django application is really running. That I just deploy in 3 or 5 simple steps. In 5 minutes, I deployed the Django application to the platform as a service. The same thing is, as I could go here, I can go to OpenShift.com as the hosted version. It's completely the same. You can sign up for free, and you can deploy free applications for free to the hosted version. You can try it. If it suits your needs, you can use it. The free version will be there forever. We just announced a commercial version that allows you to scale up to 16, and there will be another packages that will allow you to scale even more. So at the moment, we are in developer preview, and we are trying to collect the feedback from the developers. So if you want to help us, and you want to spin up some applications you want to work on, and you don't want to worry about the operating system or the configuration, you can use OpenShift and deploy these applications for free.
Yes. Please wait the microphone.
If I wanted to install different packages, do I have to go through cartridge, or could I just SSH into the...
What package you mean?
Well, for example, something a simple library such as, I don't know, RDFlib, for example.
If you need a system-level libraries like RPMs or something like that, then you cannot do it really, because it would interfere with the other applications, because the basic operating system is shared. But you can SSH into the applications and compile the libraries yourself, and then link to these yourself compiled inside the application hosted in OpenShift.
Well, it's not a system library, but for example, a different framework such as Pyramid.
Yes, definitely. There is a simple file. I can show it here. GitHub.com/OpenShift. There is the source code for the application and for the OpenShift, and also these templates, and there is a cartridge that provides the Python 2.6 support, and in here we have a setup PI. So here you can set what packages you need to install, and pip will install them for you. So this is part of the application that is inside in your repository. So you configure the application using this file, you put it into the repository, you push it, and the platform will look up for the file, see what packages you need installed, and install them. Does it make sense?
Yeah, I totally.
Awesome. So I think I'm running out of time, right? 3 minutes, but I think I'm done right now. So I will switch back to the presentation. From the beginning. So, thank you for your time. Thank you for the presentation. Also, please for Padraig, because his presentation was much longer and much more intensive, right?
Are there any questions?
May I just a few more words? Yeah. If you want to sign up, you can use the OpenShift.com website. You can sign up for free. We just take your email and your password. Oh, not your password, but you set up some password. and you can deploy free applications for free. I will ask you just to add the promo code EuroPython. You will find this information on the leaflets that my colleagues will give you if you will leaving the room, they will be there. You can just take the leaflet. There's the information how to use the command line tool, where to find the OpenShift.com, what promo code you can use. So if you are interested in the platform, just take the leaflet. You will find all the information there, so you can start super easy. That's all.
Okay.
So questions, please.
Any questions?
For both of us.
You said that this is running on EC2 at the moment, is it? Oh.
Right, the hosted version is running on EC2, so it's hosted by Red Hat, and you can use the same source code to run it yourself on your hardware if you need. We will be in the future. We'll be providing a product that will be supported by Red Hat if you need to run the platform as a service on your hardware for the commercial, medical, or some governmental stuff that needs the certifications and the security not provided in the public clouds.
Yeah, so I have a question related to OpenStack. What are the currently best automated installation methods? Because in the documentation, only the die deploy is mentioned, and I'm wondering if it's still the recommended method.
Yeah, there's a few different methods. If you follow the links in my presentation there's it depends on your distribution. Like if you're concentrating on, say, Red Hat distributions like Fedora or RHEL, if you follow the wiki, there's a set of guides there, and that's continually updated as the packages are updated. So that's up to date. That's like running through that guide takes, if you want to install all the services on a single node, would take, say, 45 minutes. That sort of time scale, and it's pretty much it's just a recipe. You just follow the commands there, and they're broken down in enough granularity to give you to give the easy functionality to split services out onto separate nodes if you want as well. There's also because of the flexibility and configuration of OpenStack, it's kind of hard to give an automated set of installed scripts, because everybody will have different needs and configuration requirements from it. But for testing, there's an OpenStack utils package in Fedora, for example, or RHEL, which gives you install OpenStack demo install, and that will install all the services onto a single node and set them up automatically, and automatically set up the databases and everything. So, and then outside the packaging side of things, there's DevStack, which is it's a big shell script for. Again, it doesn't use packaging infrastructure. It pulls the code down directly and installs it directly on your system like that. So they're the main installation vectors.
It's pretty simple to set up it on your own machine. I'm total noob with OpenStack, and I did it in 30 minutes to deploy the OpenShift on OpenStack, so it didn't take so much time.
My question is for OpenStack. What kind of issue tracking systems do you use, and also how can you do quality control, for example, for 4 weeks iteration?
Sorry, I missed the first part of the question.
Okay, what kind of issue tracking systems do you use? Issue tracking tools?
What issue?
Yeah.
So for the project itself, upstream issues, bugs and stuff like that.
Bug and also issue tracking.
So you can, like if you're consuming the Fedora packages, bugs come through the standard Bugzilla system, and the issue tracking system in the upstream Fedora project is hosted on Launchpad. So and that's fully integrated through Gerrit as well. So you can, as the patches come through, you can click through to see what bugs that through the Gerrit system that the patch addresses, and then as it's committed, Jenkins will automatically push updates to Launchpad, the Launchpad issue tracker. So it will automatically say fix, release, and set the state on the bug.
And for the code control for 4 weeks iteration, for example, how you can manage and plan the iterations?
Quality control.
Yeah, I know, it's very big question.
That's kind of dependent on your own. It's dependent on your own installation. So like people could be just installing on a couple of nodes, or you could have it could scale up to the CERN scale where you're installing 15,000 servers. So that's kind of installation dependent.
Hello. Yeah, my question is that for OpenStack, you said that the number of lines of code was something on the order of 300,000. How do you deal with such a massive project?
That's fairly small from stuff. From a Python project perspective, I guess it's quite large. Looking at the code, the code has it's actually quite easy. Like personally, I just looked at the code and I had my first patch in a couple of days. I found an area that I wanted to improve, and you don't have to get your head around all the code. You can concentrate on particular areas. Like networking is not my area, for example, so I've no idea what's going on in 50,000 lines of the code, but it's quite easy to jump in, and I have to say that the OpenStack community, it's a very welcoming community. Like my first patch was a bit bananas, to be honest, and they gave very good feedback, and within a couple of days it was integrated. So it's from a development point of view, it's actually quite easy. You don't have to get your head around all of it. You can concentrate on a particular part. And for the code itself, it has a consistent structure because it's gated. The commits are gated on PEP 8 style things, and it runs pylint checks as well and stuff like that. So the code is it's nice and consistent to read.
Any other question?
If you have any questions, we will be at the table Red Hat in front of the building. So if you have any questions and don't want to ask here, just come by and we will answer it there. Right?
Okay. Thank you very much for your contribution. Okay, I would like to remind you that we will have a coffee break now, and it will be held at 10:30 in the hotel.